Okay, our next speaker is Alessandro Zanardi. His talk is about structure and solution of urban driving games. Alessandro did his bachelor studies in Italy, Politecnico di Milano, and then moved to Zurich for his master, and is also where ETH Zurich is also studying towards his PhD. Alessandro, thanks for your work organizing, and thank you for presenting now.
Thank you very much, Saverio, for the introduction. So today I'm going to talk about the structures and solution of urban driving games. I hope this will be also a kind of wrap up of what I think, having been working on these topics in the last year, I want to highlight some of the aspects that I found interesting and that I find to be still unsolved. So I'll start with a bit of motivation, and this is the standard, let's say, planning pipeline, where you have a perception module, which is identifying and classifying the objects around you in the world. And then oftentimes this is fed to a prediction part, which is predicting where the other agents are going to be in the next few time steps. And then there's a planning part, which takes this representation of the world and you have the ego vehicle planning accordingly. So the claim here, and this was highlighted also in, I think in Mac's talk, is that this leads to passive behaviors. So you can see here, let me try to go slightly back. So there's here this vehicle, which is an autonomous car. It's a vehicle from Waymo, and there's behind here, you will see that there's appearing a human-driven vehicle, and they try to merge. You can see that without any problem, the human-driven vehicle manages to squeeze in between the cars on this lane, while the other vehicle, which is here, it gets stuck. So, all right. So the thing is that the resulting behaviors are passive in the sense that you're going to be always subordinate to what the others are going to do. And maybe this can be still fine if there are very few autonomous vehicles on the road, but still already now we see that this highlights some problems. Of course, on the other hand, you cannot ignore the predictions, because then your behaviors will become a bit dangerous. So I think that the paradigm shift that we need is from predicting what the others are about to do to predict what the others are about to do condition on our actions. So somehow we need this kind of theory of mind, or at least we need to take into account explicitly how the others would react to our ego actions. And this is where game theory comes in. So the setting, I think if you have been here for the whole day, you now should have a pretty good idea about the general setting. So, what game theory brings to the table is this ability to deal with strategic decision-making for multiple agents. At first, as you enter the field, at least to me, many of the assumptions that seem very idealized, and you have the feeling that okay, probably they will never work in reality, but it turns out that most of them can be relaxed, and also most of the computational issues, we know that hardwares and the platforms are getting better every day, so there's hope. Also, game theory, I would say it's an ancient branch of mathematics that was originally coming from economics, and so far not so much has been explored for embodied agents, so for robots. So there's hope, And the proof for this is that there are many works that actually are dealing with this nowadays. And you can see that there are works here, I just mentioned a few, but there are works that deal with racing scenarios, with highway merging, track platooning, common intersections. And they all look at this problem and try to find solutions, either using Stackelberg solutions, trying to find some approximations for the dynamics, and so on. What is in common for these approaches is that they all have most of them start off from a generalized Nash equilibrium problem, which is the one that we have seen also in Mac's talk. So before going into details of what I'm going to present today, I want to first highlight what is the kind of game theory that we actually, what are the characteristics that are needed for urban driving. So the first clear observation is that it's very different from racing, because it's not adversarial. So you're not trying to get the most, or let's say overcoming any opponent, but you are actually you have your personal objectives, and then you have this interlacement of players that is given by some common desires. So if we look a bit more in detail also for what we have learned today, we can classify racing games as zero-sum games. So on one hand, you have a winner and a loser, or you have multiple winners and losers, and this can be also formulated, I think, in Alex's work. This can be formulated as a general sum game, but conceptually, at least conceptually, this is a zero-sum game. So either you win or you lose. And the scenario is adversarial in the sense that you're trying to maximize your reward and minimize the opponent's one. On the other hand, we have on this side the urban setting, which can be seen as a general sum game, because everyone has its own personal interest, in the sense that everyone has his or her urgency of the day, where he wants to go, the kind of driving style that he or she prefers. And at the same time, the scenario is not cooperative in the sense that the agents are self-interested. What are the other aspects that I think are relevant for urban driving games? And the thing is that the problem of driving and decision making is a multi-objective problem. So you have many things to minimize or maximize. You have multiple, let's say, desiderata that you can treat as constraints or not. And you have, let's say, you have a complex environment which enforces you to take some complex decisions, which have serious implications in the sense also of liability problems. So, you cannot afford to collide with someone where you are at fault. And this is an example on the right, to give a bit more practical example of what are all these objectives that come into play when you look at the task of urban driving. So this is taken from a paper from Motional, one of the company that is working on autonomous driving. And these are the things that, or let's say, you can see each of this block as a corresponding rule or objective function that is taken into account at the planning level to make decisions, to take decisions. And you can see that these are organized into this this graph or this poset. So it starts from the up, which are the most important one, and then it goes down to the things that are less important. So you want somehow to have this hierarchy of importance for different rules, which actually promotes some sort of liability or smarter decision making. Sometimes you don't want to put all constraints and objectives at the same level. So this being said, I want to present this work, which is urban driving games with lexicographic preference and socially efficient Nash equilibria, where we described a bit more precisely what we intend by urban driving games. And we will see that with very few assumptions, this actually turns out to have a potential structure, which enjoys some favorable properties. For example, we will see that they actually exist, socially efficient Nash equilibria, and you also can guarantee convergence for IBR schemes, so for iterated better or best response schemes. So what is the main difference from related work? The main difference is the following, that many of the related works take the generalized Nash equilibrium problem that you have seen in the previous talk, where you have these constraints, scalar cost functions, and things like dynamics and collisions are all taken into account as constraints. Now we consider instead a slightly different, let's say, reformulation of the problems. So we consider the agents having only hard constraints on what they are their physical limits. So, how much you can accelerate, how much you can brake. And then you have, of course, the dynamical constraints. So all the things that are given by the physics. But then all the objectives are organized in a preference structures. What do I mean by that? By that, I mean that you have given certain actions for the players. In abstract terms, you can think of having an outcome. And then you can organize this outcome. You can, sort this outcome based on this hierarchy of objectives. Okay, so let me get into the details. So we start a bit of refresher. Here it's in continuous time. So actually I think it's a good example of a differential game, something that we, has not covered in the tutorial. So we have the dynamic of the game, which is a differential equation, where there's the state, which in this case is the state of the game, and you have the actions from all the players. Now you have then strategies. So what is a strategy for a player? Here in this case is a feedback law. At least if you do feedback on the state, you have a feedback law, or it can be simply a function of the initial conditions if you're looking at the open loop solutions. So open loop solutions, meaning that given the initial state, you're looking to a sequence of input for the next few steps. Then we have a cost, which is generally made up by an incremental part and a terminal cost. And the solutions to this is the standard, I think by now you know it very well, it's a Nash equilibrium. So this kind of strategy profile where no player has an incentive to unilaterally deviate. The problem with this general formulation is that it's quite complex to solve, at least in fully generality. And the solutions, the tools that you have are listed here, these two, which are the minimum principle and dynamic programming approach, where in both cases to actually are more some, let's say, to some extent, they are tools to actually check whether you have a solution or not. Because even in dynamic programming, it's a constructive approach, but still you have to guess the form of the value function. So in most of the, in some cases, for example, in LQG, this works fine, but in the general case, it can be a bit intractable. But we will observe that actually, games that have a certain structure are easier to solve. So what is the structure which is peculiar of urban driving, or at least driving games more in general here? So we have the dynamics of the players, which are independent from each other. Of course, each agent has its own dynamic. Then we have a communal cost here, which is a communal payoff for the players, which in this case is the desire of not colliding. Then there is a personal payoff, which in this case is you can think about it as a cost term on time, on comfort, whether or not you reached your destination, or in the case of racing, whether you are ahead of the opponent or not. So in this case here is still joint. It could be joint state. And then we organize this, the first step is rather than treating this as a communal, as a constraint, we actually organize the preference of the player as a lexicographic preference, where in the first, let's say, element of this tuple, we have the objective of not colliding, and then we have the personal objectives later. And of course, this is made a bit for simplicity, but you can expect this can be generalized to n optimization terms. So a bit more in detail for each of the terms. So what do we mean by communal collision cost? Well, communal collisions cost, intuitively, it's something that if it gets better for me, it gets better also for the others. So if I don't collide for you, it's also better for you. So this is a condition that we actually need to prevent some kind of ill-posed cases such as suicidal vehicles and so on. And in practice, there are many cost functions that would satisfy this, this condition. If you can think about having the same type of cost for all the players, or the same class of functions for all the players, those satisfy this condition. So some examples could be kinetic energy transfer, where you have where you take into account the product of the masses of the two vehicles, or just a simple indicator function whether you're colliding or not. So here, just to clarify, J collision of IJ is the collision between agent I and agent J. Of course, there are some cost functions that actually violate these conditions. For example, if you take into account whether your collision is at fault or not, you cannot guarantee to satisfy this condition, even though in practice it works quite well, almost always. What are the other differences? So we have seen that for this personal payoff, we can actually distinguish between two cases. One is the case of racing, where it depends on the joint state, and the other one is the case of urban driving, so the one I will talk about today. And in this case, we actually have this term here, this guy, which depends only on its personal state. And then again, we have this lexicographic preference, where we have we sort the possible trajectories or the decision making, where we first care about the collision objective, and then only then we actually try to minimize the personal cost. And the claim here is that this setup is it naturally comes, first of all, it's always well posed. So you can imagine that also if, someone that has not seen you, or some suicidal person jumps in the middle of the road, you don't have any constraint, but you would actually find a solution that tries to minimize the collision harm, and so irrespective of the personal objectives. While if you compare this to having a weighted sum in the cost functions, Either you would result in an infeasible solution where because you cannot satisfy the constraints, for example, of not colliding. Either you would find a solution which might be a bit of a trade-off between other objectives that actually do not matter in that occasion. So to sum up, here are the characteristics of communal urban driving games, where you can see the only difference between racing and urban driving games is that in the personal payoff, actually, here the state depends on the personal state. So what is the first result? The first result is that given these very few assumptions, actually we realized that this game has a potential structure. And the potential that is actually minimizing the potential that is associated to this game is actually minimizing the social cost, so the sum of all the objectives. So here you can see on the right, you have this all this continuum of Nash equilibria, which is the same that Mac was discussing. And the potential function actually gives you a specific solution to this problem, which I haven't really compared it to the normalized GMP for solutions, but I would expect that they are somehow close. But here what you have is that since the potential function is the sum of the cost of all the players, this is actually exactly minimizing the social cost. So a bit more in detail, this you have seen it also this morning. So we have a potential game, so meaning that you can associate a potential function to the game, which if a player decreases his cost, it also decreases the potential function. So in this case, it's there's a slightly different notation because actually here we are improving in a lexicographic sense, and this will be more clear in a few slides. All right, this is just a repetition. The proof, it's very, once you show that the potential associated to that game is isomorphic, at least to the social cost up to some constants or scaling terms. Then you have that the strategy profile minimizing the potential is a pure Nash equilibrium by definition because it fulfills this condition. All right, so what is the next nice consequence about this is that we can guarantee that iterated better or best response actually converge to a Nash equilibrium. And here there are some technical terms. So for example, here you see that it actually converges to an epsilon Nash equilibrium because for continuous spaces, there are some pathological cases in which you could converge to a limit sequence, which is actually not a Nash equilibrium. The kind of tricky thing is that in principle, if you pick an arbitrarily small epsilon and you're optimizing continuous space over continuous spaces, you can actually guarantee to converge to an epsilon Nash equilibrium. So something that you cannot improve by more than epsilon unilaterally deviating. And this is just the algorithm version of iterated better response, where you have the best response or rational reaction set. Of course, if you look at the discrete strategies, all these epsilon things go away, and you are guaranteed to converge to an equilibrium, which is not necessarily the one given by the potential solution. I give you just a little bit of intuition so on why this is true. So we have on a logical sequence, we have that UDGs we have shown that are potential games. So we have that if a player improves by epsilon, we have this potential function that also improves by epsilon. therefore, if each player improves by epsilon, this potential keeps decreasing, and then you actually reach convergence. And this is a bit, I think it was worth highlighting what it means to actually improve in a lexicographic sense. So here, if you just take into account two objectives, where you have collision and personal cost, and you have that collision as higher priority than the personal cost. So it means that actually when you move in this direction, so you are decreasing your collision cost, it could be that your personal costs are going up. Nevertheless, if both these functions are bounded, you can guarantee that if each step is at least epsilon in a lexicographic sense, this sequence of steps will converge. So what are the bit of sum up of the results? So the first thing is that we have that a pure Nash equilibrium is guaranteed to exist, which it's nice to have, because we have seen this more. We are seeing this before in the tutorial that this is not true for general games. So you actually, the famous Nash theorem actually says that it exists. It always exists as solutions in mixed strategies, at least for games in matrix forms, or while in this case we have a solution in pure strategies. The other, let's say, the following important fact is that this pure Nash equilibrium are somewhat easy to compute, or at least and as hard as solving a nonlinear optimal control problem, because you actually only need to minimize the potential. And the result is that if you solve this optimal control problem, this gives socially efficient equilibrium, in the sense that it also minimizes the joint cost for all the agents. And of course, again, we have best response iterations that converge to multiple Nash equilibria. And if you're uncertain about which player you're going to be in when you enter an intersection or another scenario, actually, this gives you a rational tool for equilibria refinement. So for deciding which equilibrium you should steer towards, because in expectation, this is the one that will give you the lower cost. So a bit more on the practical cases. So in the paper, you can see that we compare the equilibria found by iterated best response and potential solution. But I think what is more interesting is actually this part, where we have that we stretch a bit, or at least we do a slightly more complicated version of the lexicographic preference that I showed you so far, where we have not only two levels, but three. So in this case, we actually first optimize for collision. Then we want to fulfill traffic rules. So for example, the ability to stay in the lane, we set a certain speed limit and so on. And then we have, only after these, we actually optimize for personal goals or comfort and so on. So I want to spend a few words on how we actually solve this problem in a sequential way. So how do you optimize in a lexicographic sense? So if you have a discrete strategies, so if you have a bunch of trajectories, then it's quite simple in the sense that you just have to sort them. It's like sorting words on a dictionary. It's a bit more challenging in continuous spaces. So what we tried, and it worked quite well, is to actually solve this problem multiple times in a sequential fashion. So here you can see that if we consider just the collision constraint and the personal objectives, we have that first we find a trajectories which is collision-free, and then given this cost, or at least it doesn't have to be collision-free, but it finds the minimum in the sense of with respect to the collision objective. And then we optimize for the rest, adding this constraint. So you have that you do not want to worsen the objectives of higher priority. And this, it turns out that it was, to be honest, when we tried it, was a bit surprisingly stable, because you can always initialize this second problem from the solution of the first one, where this is satisfied, where this constraint is satisfied. Another thing that you can actually try to solve this kind of lexicographic problems is taking multiple values for this guy here. So multiple, in this sense, bottom values for this constraint, and then try to solve this problem in parallel. And this would give you, a certification. The first problem that you managed to solve, it would certify that you have at least this level of satisfaction for the objectives of higher priority. So these are some example results where you can see that here we put a vehicle which got stuck and forces these other vehicles to actually violate the lane. So it violates the lane and they kind of merge back in. So let me show some more in detail, some examples of the trajectories that we find in this case. So here green, the semantics is the following. So green is actually where the vehicle is accelerating, while the colors more towards the red is where the vehicle is slowing down, is braking. And you can see here that, for example, to violate as minimum as possible this traffic rule, these two vehicles that here have no reason anymore to accelerate or brake, because here at the beginning of the interaction, here we initialized in a let's say in a hard scenario, but here at the beginning of the interaction they are braking or accelerating to actually avoid collision. Here instead there's no reason anymore to have such a behavior, but they still, these two vehicles that are forced out of their lanes, they actually first accelerate and then merge back in to not violate or at least to violate as less as possible this constraint. So, and in the paper, we compared this, the solutions found with the minimizing the potential functions with the one obtained by iterated best response. So here, I will not go into details. If you're interested, you can actually check them out in the paper. But it turns out that even empirically, where in this case, we don't have any guarantee to find a global optimum while minimizing the potential function, because it's a it's a nonlinear, multivariate nonlinear problem. So the solutions that you can find are as good as your nonlinear optimization tool. But still, also in these experiments, we find out that also empirically the solution found by minimizing the potential function had nicer behaviors than the ones that you find through iterated best response, which tend to be skewed in favor of some of the players, in particular, considering the ones that start first or play last. Okay, so, and in this sense, this is what I mean by the potential solution is the most rational, in the sense that in expectation, if you now think about, okay, this intersection, I will not do only a single intersection, but I will play many intersections in my life, or many merging scenarios and so on. Actually, the potential solution is, minimizes the expected cost. So what are the conclusions here? We have that we have seen that urban driving games are actually general sum games with a comprehensive structure, and very few assumptions are actually needed to obtain a potential structure. And this actually has some nice guarantees. So we have seen that it exists pure Nash equilibria, and they have existency and efficiency guarantees. We have convergence of iterated better response. On the practical side, we have that instead of having n coupled optimal control problems, we can solve for a Nash equilibrium solving a single optimal control problem. And this is the last comment I just made in the slide before. This is also represent a rational tool for equilibrium refinement. Also, we have seen that this was to some extent our first step in the direction of having the agents expressing arbitrary preferences on outcomes of the game, rather than formulating a single scalar game with, let's say, a weighted sum of objectives. So to conclude, I want to remark what I think are very interesting topics for the future of this, say, game theoretical motion planning. So first of all, we have seen that in many cases, we have all these examples where we actually deal with, you know, a handful of players, you know, from 3, 4, but actually as humans, we're able to deal with this kind of examples. So I think there's some kind of research that, you know, needs somehow to find a nice inherent structure of these local interactions to decompose the bigger problem. Another aspect that has not been taken into account so far is that we have seen this, or at least not, I haven't seen many works on this, maybe that there might be around, is that instead of only having this kinodynamic optimizations kind of at the low level where we take into account nasty nonlinear effects of the dynamics of the players, which I think could be very relevant for racing scenarios and so on. But I think that maybe for scenarios as urban driving and so on, we can somehow look at aspects a bit more at the high level, you know, which go a bit more in the direction of sampling-based trajectories. Or these are, you know, are in order of increasing complexity, at least to what I perceive. Something that we need to do to deploy this on real cars and so on, it's actually to take into account these aspects of having bounded sensing and computation. So there are some few works in game theory that actually look at how human make decisions, which you know, is not necessarily a good thing, but there are this concept of bounded rationality. So somehow, often you are okay with settling with a good enough solution, which in many cases for our scenarios could be a valuable option for real-time implementation, especially if you're, you know, running many other things in parallel on the same car. And last but not least, I think a proper inclusion of uncertainty in this game is a very deep concept, because on one side, you have this game theoretical formulation where you want to, you know, take into account how the others are reacting to your actions. But on the other hand, you have this liabilities issues. So for example, if something bad happens, you cannot say, oh, but I thought that you would have reacted in a different way, or this kind of problems. So I think there's there's a very much open problem here, or very open field of research that actually should look at how we should, or it should be incorporated these uncertainty aspects in the games. So with this, I conclude. Thank you for listening. I hope you had fun during the tutorial.
Thank you, Alessandro, for your presentation. There's actually a question. I'm not sure if you have the document open. Maybe you can address that.
Give me a second that I close this.
Or I can also read it to you for the recording as well.
Yes.
The question is about the comparison between the potential Nash equilibrium, so the Nash equilibrium that minimizes the potential, and the normalized Nash equilibrium from the previous talk.
Yes, so we didn't do it. It's something that I would expect that they find similar solutions. So in the normalized Nash equilibria, you have this, that all the Lagrangian multipliers are equal. So in principle, now there's also Simon online, so he might correct me if I misunderstood, but the solution that you find as this, this fairness is sharing these Lagrangian multipliers, which is not the same with minimizing the social cost in the moment in which you don't have the same cost for all the players. So you might have different shapes of the functions and so on. But in principle, I would assume that they are somehow similar, in the sense you have seen that also in, if I go back, let me try a few slides. Also here you have all these gray trajectories, which are actually all pair of Nash equilibria, which gives this continuum that also Mac was talking about.
Yeah. So in general, I think it's just a follow-up comment on this. I think it's very interesting to see how many Nash equilibrium one can actually find, right, in these games, or whether the topic of Nash equilibrium selection or which Nash equilibrium to promote as the solution of the game, it's a multifaceted problem.